Good evening, gentlemen.
Hi, Richard.
You
Hey
there,
there.
Gerald? All right. Can you
Hi
guys
there.
hear me properly?
Yep.
Do I
I
have the
hear
right?
you properly.
I have the
You,
right microphone this time.
you,
Oh
Sounds
you
like
are
it.
yeah.
you are
Yes, I
proper.
do. I am proper. All right. Very good to hear. Well, good evening, everyone. I'm Rich Ozer, and Gerald McKeegan and John Curry have come into the observatory tonight and to show you stuff.
Weather looks
Yeah.
great for tonight. We've got very low
Yeah,
humidity.
yeah.
Yeah, so
It,
we've got a bright moon tonight, so we're going to be looking at bright things because we really don't have any choice. But the moon is always fun to look at. We'll at least look at the first and second brightest things in the sky tonight, and then see what offers itself up for the rest of the evening. But before we get started, I want to remind everybody that we are at the Chabot Space and Science Center. We're at the 36-inch reflector, the research reflector, fondly as known as Nellie. And we count on you and all of our supporters to keep things going here at Chabot while we're still closed for COVID. We're still planning on opening up in the fall, and we're crossing our fingers that that stays on schedule. Chabot is doing small events now for private parties, and so we're trying to get back into the swing of things, but we do need community support. So please, please donate. There's a donate button for those on the Facebook page, and there is also a link that will take you to the Chabot website if you're interested in donating that way. The Chabot website is chabotspace.org for those of you who are on YouTube. And we hope we can count on your support. And we want to thank Fremont Bank, one of our community supporters, for their efforts to keep Chabot running through this difficult time. So, anyhow, now let's move on. And I think the first thing we're going to look at tonight, Gerald, is the Orion Nebula because we still can. And
well, actually, Richard,
yeah.
the first thing we're already looking at, and that's this thing right here.
Oh
Yeah.
yeah, there
That's
we go.
the moon.
Yeah, yeah. Oh,
There.
Get in the
that's
way
right.
there.
We're already looking at it through your camera.
Yeah, yeah.
That's funny. Well, why don't we see what's in the telescope? So I'm going
Okay.
to go ahead and
All
share
right.
my screen.
So we're looking
And
right now at the Great Orion Nebula.
there we go.
All right. So if you
And
look,
we're going to go ahead and take some longer shots here. This is
okay.
just a 10-second one. And
Well, while you're
I'm going to
doing
go
that, I
30
tell
seconds.
people a little bit about this.
Mhm.
If you go outside right now tonight here in the Bay Area and look in the southwestern sky, about halfway up, you will see the constellation Orion. And Orion is distinguished by a couple of bright stars, Betelgeuse up in the upper left and Rigel in the lower right. And in between the two of them, you see three stars all lined up. Those are, we call the belt stars, representing the belt of Orion. And just below the belt, you'll see a faint string of stars we call Orion's sword. And in the middle of the sword is this huge cloud of gas and dust that you see in Richard's image now. This is a cloud of gas and dust about 1,300, 1,400 light years away, and it is condensing and it is forming new stars. And so what we see in the cloud are a number of very young stars. In particular, you see four very bright stars, kind of a little bit to the right in this image. That's what we call the trapezium. These are all stars of the classification either O or B, which means they're very massive stars and they're extremely hot. They're very young. O and B stars don't live very long, so that kind of by definition makes them young.
And they're so bright that in that image that they almost blur together there as one
Yeah.
big star.
I'm going to
but
take a
they-
shorter image so you could tease those apart a little bit better.
Okay, okay. So those stars formed from this huge cloud of gas and dust, and they went through a period of condensation, just the cloud kind of swirling around a local dense spot. And as it swirled around and got denser and denser, eventually the protostar formed. The protostar is just a very dense ball of gas that's getting progressively hotter and hotter. Eventually, enough mass falls on that protostar and it gets compressed and hot enough to where the fusion process starts. And that's how stars are born. When a star first turns on, when that fusion process first starts, the star then begins to actually blow material away from it. So prior to that, it was condensing material was falling onto the star. But once it turns on, then it begins to radiate energy outward, which actually creates a force that slowly pushes the condensing cloud of gas away from it. And so that has happened with these 4 stars. They have now produced enough radiation that it's pushed the gas cloud away from them, producing a pocket within the gas cloud. And so if you look carefully, you can actually see that pocket surrounding those 4 stars. There is much denser regions all around, and other new stars are forming in those denser regions. Most of those new stars are less massive than the trapezium stars. They take a little longer to form, but and they won't be nearly as massive. But the neat thing about those stars is because they are lower in mass, they live longer. So the trapezium stars are going to have a relatively short life, probably less than 10 million years on the main sequence. But the smaller stars within the cloud that are still forming, those stars may have only 1 solar mass or even less than 1 solar mass, and they will live for 10 billion years or longer. So the lower the mass of the star, the longer the star lives.
Do you want to talk about the significance of the color?
Sure. So you see predominantly 2 colors, kind of a turquoise green or blue, depending on how your eyes are calibrated, and then a kind of a pinkish red color. So this cloud is mostly hydrogen. And when you ionize hydrogen gas, it glows in a very distinctive reddish color. It's kind of a deep red color. And so that pinkish hue or reddish hue that you see there, that's primarily from ionized hydrogen. But this cloud is composed of gases and dust left over from previous stars, and some of those stars gave off oxygen when they reached the ends of their lives. So there is a small amount of oxygen in the condensing cloud. Oxygen, when it's ionized the right way, glows very brightly in this kind of a turquoise green color, turquoise blue color. And so you see that kind of closer into the trapezium stars. It's a special kind of ionized oxygen. It's not one we normally encounter in laboratories. In fact, when astronomers first saw that, they weren't sure what it was. They saw this kind of greenish blue cloud in a lot of nebulae, clouds of gas and dust out in space. They saw this color, but they couldn't relate it to any colors that they saw when they did spectroscopic analysis of gases in the laboratory. And it turned out that this was a special kind of situation where under conditions of very low pressure, essentially a vacuum, when you ionize oxygen, you get it into a different ionization state that actually produces that greenish blue color. So we call that oxygen 3 nowadays, but when astronomers were first observing this, because they didn't know what the gas was, they gave it a new name. They called it nebulium. So it was a gas in a nebula, so they call it nebulium. So today we know that it's actually oxygen.
Gerald, we have a question here. Is it, I give you the answer. The question is it possible for Nellie to see 6 stars in the trapezium? And the answer is yes. We often do that. In fact, we use that as a kind of a measuring device when we're looking at M42. If we can see 5 stars, it's a pretty good night. If we see 6, it's a really good night.
Right.
And
right.
yeah, we can see them without a camera, actually looking through the telescope.
See them better without a camera, actually.
Yeah. The
Yes.
problem, yeah, if you want to see the color, you're going to end up overexposing the trapezium. And if you, what you can see here on this image,
I can see one of them
you
anyway.
can certainly see the elongation here. That's 2 stars. And it's harder on the one next to it.
Yeah,
you could probably bring it down a little bit.
Lower one there, you can just barely make it out at about the 7 o'clock position relative to that bottommost star in the trapezium.
Let's just see.
And again, for those that are asking, this is the Orion Nebula, or M42, that we're looking at right now.
Now, in addition to the trapezium, you see some other stars. Notably, you see 3 stars lined up in this field of view. And often when people first look through our telescope at the Orion Nebula and they see those 3 stars, they assume those are the 3 stars that are the belt of Orion. But in reality, the field of view that we're looking through is very small. It's only a small portion of Orion's sword, which is far away from the belt of Orion. Those 3 stars just happen to be similarly lined up. You wouldn't make this out at all with the naked eye.
All right, so you can see right here.
Yeah, a little bump there.
That little bump is the companion to the brighter star. And here, Gerald, I think I wouldn't have picked it out if you hadn't said anything. But yeah, at the 7 o'clock position, there's a bump there, and that's about as good as we can get with the camera system.
Yep.
Gerald, there's another really good question here. If you're going to continue on about your discussion of the colors, is the red cloud in front of the turquoise cloud, or is it like looking inside a bubble?
Yeah, it's more like a bubble or a pocket of gas. So the trapezium is surrounded by gas, basically kind of like 3 sides, and we're looking into the pocket. So the green or bluish green color is sort of the inner part of that pocket, and then the pinkish stuff is farther out. So you have to kind of imagine this as a 3-dimensional thing. If you want to go back to one of your longer exposures, Rich.
I will in a sec. I do want to point out though that now
there it is
very clearly that there are 6 stars here.
Yep.
And also the red doesn't travel as well as the greenish blue color there.
Right.
It's not as bright.
Right.
As a result, doesn't.
And again,
long distance.
That cloud is mostly hydrogen. So the oxygen, although it glows very brightly, it's actually only a small percentage of the total amount of gas in the cloud. So it's kind of deceptive when you see all that blue-green color there. You want to think, oh, that's mostly oxygen. But actually, even that part of the cloud is mostly hydrogen. It's just that the hydrogen does not glow nearly as bright as the oxygen does. All right.
Sorry, yeah, I'm going to have to actually take another one. It's not loading the previous image for some reason.
Okay.
So that's all right. I'll do that again.
All right.
We could spare the 30 seconds.
Yeah, one of the interesting things about cameras versus your eye, if we put an eyepiece on this telescope and invite you to come up and look through the eyepiece, which eventually we're going to get back to doing that.
We hope at least.
When you look with your eye's dynamic range, its ability to go from bright to very dim is much greater than the camera's. The camera can't quite resolve that huge range of brightness, but your eye can. So when you look at this with your eye, you see the trapezium stars very distinctly as points of light, bright points of light, but you can also make out those other 2 stars on a good clear night. You can make those other 2 stars out very easily, and they're not lost in the glare of the bright stars.
So Soren asks, so those stars are stationary? Well, no stars are stationary, really. They're about as stationary as any other star.
Yeah, they are relatively close to each other. I think the total distance across the trapezium is only about 5 light years. So they are relatively close to each other. They're not all in the same plane of sky, though. So if you imagine, the screen of your computer, that's a two-dimensional image, and there's a tendency to want to think of all four stars as being on that same two-dimensional plane, but actually this is a three-dimensional image. So some of those stars are farther away than others. So you got to kind of imagine if you could orbit around it, you would see that they are at different distances from the Earth. They're still pretty close together, but they aren't all exactly the same distance.
And all of these are part of the Milky Way galaxy, so as such, they are orbiting around the center of the galaxy, like all of
Right.
the stars.
So the big lesson here is that nothing is stationary.
Right.
Right. Yep. And we can't really tell you, a motion relative to a given point. We can only tell you motion relative to another moving object. So, motion relative to the Earth or motion relative to the sun. But the Earth and the sun are also moving. So everything is moving out there in the universe.
Now those double stars in the trapezium, they have very long period orbits around one
Yes.
another.
Yep.
I mean, we're
Yes.
talking hundreds, if not thousands, of years.
Hundreds of years. Yeah.
Hundreds
Yeah.
of years.
Yeah.
So so they're not stationary with respect to one another either. So
Right.
you'd have to be looking over a whole lifetime in order to notice any of that motion.
All right.
Yeah.
Okay.
I guess so. That's the second brightest object in the sky tonight.
Shall we go to the first?
I think we should probably go to the first.
If for no other reason to
yeah.
show them why it is astronomers never look at the moon.
Yeah,
we have a full moon, right?
That's right. We have a full moon, and, but it's not quite full. It's gonna be full tomorrow, but it's full enough. It's called the worm moon this month.
The worm moon. I haven't heard that one.
Worm moon is what I read.
When the worms start coming out of the ground.
I have no idea what that's. Yeah, they come out of the craters. I have no idea why it's called the worm moon, but that is what I read today.
Yeah, a lot of those terms come from actually Native Americans. They would give names to the different full moons each season based on what was going on that season. So like there's a spring moon and there's the snow moon, which would be in the wintertime. So you have those. See, is that the star I see there? It's not very.
Well, it's a nice double. What is it?
Yeah, well, it's supposed to be it's supposed to be Algebra.
Oh,
I'm not sure that's what I'm actually looking at here. Let me go to.
Can you see any color?
Yeah, let me go to Regulus here and see what.
Yeah, it looks like there is one's blue and
yeah,
one's white.
Algebra is a double star. So.
Yeah, that is what you got there. Why don't we get it centered? Whoop. All right.
I'm sorry.
That's okay. I thought that was kind of a neat one.
Yeah, that's what I thought. It was the one over to the side that was the.
Oh, so the moon was named after earthworms that appear in the soil in the springtime as the soil warms up.
See,
okay, there you go.
I knew that. Okay, now we're on the star Regulus in the constellation Leo, and that's kind of a stop-off point before we head over to the moon.
Because we didn't think we'd find the moon?
Yeah, well, I want to make sure the telescope is pointed accurately. Okay. Here we go to the moon.
Just kidding.
To the moon, Alice.
So many people don't know what that refers to.
One of the great classic comedies of the 1950s.
That is bright. Let me
yes.
fix the exposure here.
Good luck getting it in focus here.
Ooh, You're blurring it up.
Yeah, I went the wrong way here.
Hey, this is
Right.
another good question that goes back to the Orion Nebula here.
That looks good, I think.
If there was a planet and you were on one, I assume a planet near one of the trapezium stars, would you see the turquoise at night?
Uh,
Well, I don't know.
Well, that is a great question.
Uh,
I don't know the answer to that. But, you know, this you probably would.
yeah, you
see quite a
probably
bit.
would. Yeah, I would.
You know, because
because it's so bright.
and this we weren't using any special filters or anything to bring out those colors. That was just a regular red, blue, green image.
But if you were that close, there's probably a lot of things that are really, really bright there. It might wash out,
including
color.
like gamma radiation.
Right.
It might be the last thing you see.
It probably wouldn't be a great place to have a planet.
Yeah.
Or to live on a planet.
Okay, well, we are now looking at the moon, and you're getting a sense why it is that astronomers don't like to look at the moon very much. The problem with the full moon is that there are no shadows on the part of the moon where we're looking. If you were standing on the moon looking back at the Earth, the sun would be almost directly overhead. You would not have much of a shadow around you. And because of that, when we look at the moon during a full moon, it's very hard to get any sense of the depths of craters or the heights of mountains and so forth. You really have very little contrast. And so it's really not much fun to look at the full moon because you know, you just can't make out much. One thing I want to do though, by the way, that crater that you see there with what looks like kind of a butterfly pattern of ejecta, that's called Proclus. It's between Tranquility and Chrysium, the two C's, Tranquility and Chrysium. So I'm going to go over here to the other side of the moon. Maybe.
How's the focus on that, Gerald? Do you want to do a quick?
I've been fiddling with it.
Oh, you have.
Yeah,
Okay.
I've been fiddling with it, and it's
I
very
know.
hard when it's all washed out like this.
It may be easier
It's just too washed out.
If you get over to the edge, it may be easier to get a good focus. Yeah.
So we are literally hours away from full moon. So yeah, we don't even have much of a terminator here. So oh well.
We got a little bit.
But like Richard said, focus on the edge itself.
Yeah, it's not too bad actually.
Yeah. Okay, that's the wrong way.
Yeah, going the wrong way.
It's getting worse.
There.
Nice.
There you go. Okay. Yeah. Okay. So anyway, as you can see, it's very hard to make out any sense at all of the depths of craters or things, but there are some interesting craters to look at. This one here with a bright splash around it, that's the crater Copernicus. It's kind of at the bottom edge of the Imbrium Basin on the moon. The Imbrium Basin is a huge impact crater, very large impact crater, which is filled with lava. This impact was so forceful that it caused the crust to crack right down to the what was once the liquid interior, and lava oozed up through the cracks and filled this whole basin. So this whole dark region that you're looking at right here, that's the floor of the Imbrium Basin, and it's just a smooth layer of lava. At least it looks smooth from our perspective. It's also darker than the surrounding terrain. So when you look with your naked eye at the moon and you see dark patches and light patches, those dark patches are these huge impact basins that have filled with lava. And this all happened, 3 billion years ago or more.
Hey, another good question from Soren here. During the Apollo mission or missions, what happened to all those vehicles? Do they erode or are they still pristine?
They are still there.
They might be a little dusty, but they're probably still pretty nice.
Probably dusty. They may have experienced a few micrometeorite impacts, micrometeoroid impacts, I should say. So, little small pebbles hitting them. So they're likely they've suffered some damage, but for the most part, they're still there and they're still in one piece. And the batteries are dead. So,
Yeah, the batteries, and there may be a really expensive parking ticket.
Yeah, probably.
We did get one question, just in general here. Is it possible to see NGC 2336 tonight? Well, NGC 2336 is a spiral galaxy, and it's a pretty dim object. And on a full moon night like this, we're probably going to avoid the dim galaxies. It's hard enough on a moonless night. Yeah.
Let's see. Erica wants to know what's the composition of the lunar lava is. It's basalt, just like lava here on Earth. It's basalt. In fact, one of the discoveries of the Apollo mission is that a lot of the moon is made up of a lot of the same kind of materials, same kind of rocks that we find on the upper part of the Earth, or on the crust of the Earth. And that has actually led us to a prevailing theory about the formation of the moon, that it formed from an impact with the Earth about 3.84 billion years ago. A protoplanet, which we've named Theia, hit the Earth, fractured the crust quite a bit, may have fractured the entire Earth, but a lot of crustal material was thrown out and went into orbit around the Earth, and that material eventually condensed and formed the moon. So the moon has a lot of similarity to the crust of the Earth. There's not as much iron because the iron is down deep inside the Earth, but the rocks that we would find on the crust and at the surface of the Earth, there are similar rocks on the moon. So that lava is basalt, just like on the Earth. All right.
Sheldon asks, are the galaxies of the local group visible this time of year? And if so, is it possible to focus on some of them tonight? Again,
yes and no.
With the full moon, it's going to be a problem.
No.
Actually, springtime is the best time of the year to be looking at galaxies because of the orientation of the Earth's orbit around the sun, and because of the sun's position relative to the plane of the Milky Way galaxy. Springtime is the best time to be viewing galaxies. So there are a lot of galaxies up there, and if we didn't have that big bright moon up there that I'm pointing to, we would try to look at a lot of those things. We may look at a couple tonight, to some of the brighter ones, but because of that bright moonlight, it tends to wash out those faint galaxies and make them hard to see. But next week, if we have a clear night again, there will not be a full moon to deal with, and we'll have a lot more success looking at those faint objects.
And the fact that some galaxies are in the local group means they're close by, but not necessarily that close by, except for Andromeda, which is really bright. The others are pretty dim.
All right, where to next?
Well, last week we looked at Ghost of Jupiter. Is it up from behind the other telescope's dome yet?
Oh, if it is, it's going to be right near the moon.
Well, it might be. The camera is sensitive in that light. We should give it a shot.
All right,
and then I can at least show a picture of the processed image from last week.
Okay, you got an NGC number?
Yeah, that is NGC 3242.
Actually, I think it's in here as the Ghost of Jupiter.
Yeah, but you've got to get it exactly the right wording on there. Last time you had a hard time.
Yeah, that's a real problem. If you don't have it exactly right, it doesn't come up.
Well, I got it right.
Hey, all right.
I spelled ghost correctly.
I'll bet it doesn't come up if you say Jupiter's ghost.
G-O-S-T, right?
Yeah,
right.
right.
Ghost.
Well, it's Ghoste, right?
Yeah, we're so funny.
Uh,
Okay, here we go. Maybe. There we go.
All right. Are you going straight there?
Yes.
Okay.
oh, it's actually not very close to the moon, so we should be all
Yeah.
All
right.
right. Let's try a 30-second exposure.
Okay. So just to make sure everybody understands, this has nothing to do with Jupiter so,
Or ghosts.
or
Right.
ghosts. Yeah.
Yeah, right.
Yeah.
The name Ghost of Jupiter was coined before anyone had any idea what this was. So it was a poetic name that we still have fun with today. But if we're able to see this, you'll recognize it as a planetary nebula, and we'll explain what that is once we have an image of it.
Yeah, yeah. Definitely does not look like the Orion Nebula.
No, it's yeah. This is still the
that
last.
image sure does.
Yeah,
there we go.
Hold on, let's get this adjusted a little bit.
Sheldon says, let's get rid of that full moon. Unfortunately, we kind of depend on the moon for a lot of things.
And also, it's going to be contributing to the increase in tide that is going to affect the event that the entire world is watching right now.
You know, somebody else asked if we could look at the Crab Nebula.
Yeah.
It's up there, but it's a pretty faint object.
That is really a faint object.
Yeah.
Gerald, can we move it
Yeah,
up a
yeah,
little
let me-
bit, and I'll
let me go-
grab another exposure once you move it a bit.
Okay. All right, go ahead.
All right.
But you have also that
Yeah.
stack of those images.
Let me show you the processed one from last week.
Yeah,
Hold on
you got to
for a
show that
moment.
off. It's a really good image.
Yeah, let me get that up on the screen. We'll let this one display
Yeah.
first, and then we'll do the processed one.
Well, you can already see quite a bit of detail on this one. This is actually looks pretty
Yeah.
good here.
Yeah, it's a good night.
Hopefully I centered it correctly.
We'll find out any second now. There we go.
Hey, there
Very
you are.
good. Perfecto.
All right.
So I can zoom in on it a little bit.
See a lot of detail in there.
Yeah.
So this is what we call a planetary nebula. This is actually the remnant of a dying star. Stars that are lower in mass, say less than 8 times the mass of our sun, they die in a very slow process. First of all, they stay for a long time on what we call the main sequence. That's where they're very stable. They are fusing hydrogen into helium at the core. They're in hydrostatic equilibrium and so forth. They're very stable. That's the main part of the life of a star. But as the star gets old, it begins to swell up, begins fusing helium into carbon, and the star gets very big. As it does so, its outer layers get cooler. So the star eventually becomes what we call a red giant. And just giving you kind of the short version of the story here, the red giant begins to lose its outer layers of gas. So the outer envelope of the star starts bleeding off, and there's some strong winds within the interior of the star that blows those outer layers of gas off. The star can easily, over a period of episodes, lose more than half of its mass. But eventually, it exposes the interior, much hotter core, and eventually also the fusion process at the core stops. And when that happens, whatever's left of the star kind of collapses down, becomes what we call a white dwarf. The white dwarf is extremely compact. It's something where, you know, a teaspoon of it would weigh as much as a Mack truck. And let's see, oh, there we go. Okay. So this is a processed image that Richard took last week. It's actually a stack of several images. Um, but anyway, just continuing the story, the white dwarf is this very compact object. It's extremely hot. It's taken all of the remaining heat of the original star and it has condensed it down into this very tight little ball. The star may have once been 1 million miles in diameter, but now it's shrunk down to less than 10,000 miles in diameter. The matter in the white dwarf is what we call degenerate. The electrons can't move from one energy level to another. So it can't really shrink very much, but it can't expand because of the heat either. So
So Gerald, are those electrons at the lowest energy level for those
they're
atoms?
it depends on which atoms you're talking about, but they're at the lower energy level and they can't move to higher energy levels.
And that's because of
Because
gravitational effects. It's very compressed.
very compressed, right?
Got
So
it. Okay.
okay, so they can't move to other levels because they'd be bumping into other electrons. So we call that degenerate matter, and that's what the white dwarf is composed of. It is emitting a lot of energy, but it's so hot, a lot of that energy is coming off not as visible light, but as ultraviolet radiation. And the white dwarf is surrounded by all that gas that it was blowing off when it was still a red giant. And that gas is then ionized by the ultraviolet radiation. The ionized gas then begins to glow because the electrons in the gas can jump to different levels. And when they jump and then fall back, they emit light. And so what you see is this glowing cloud of gas surrounding the white dwarf. And you can just barely make out the white dwarf at the center of the ghost of Jupiter. You can also see a shock wave. This whole process that I'm describing to you happens in episodes of contraction and expansion and so on. And those episodes cause shock waves within the cloud. So you can see that shock wave that's kind of looks like a torus within what looks like a bubble of gas. Very common to see it that way. Planetary nebulas can take a lot of interesting shapes, but it's all basically the same process that's involved. This gas will slowly dissipate, slowly expand away from the star and dissipate, and eventually just drift off into space and join other gases from other dying stars and form new clouds, which will then condense and form new stars. The white dwarf continues to sit there slowly cooling, and I mean really slowly cooling. It can take billions of years for it to go from, say, 20,000 degrees to 10,000 degrees. And eventually they will lose their energy and become what we call black dwarfs. So they're not black holes, they're just big lumps of matter out in space, 10,000 miles in diameter. They're no longer emitting light, so we call them a black hole, or I'm sorry, a black dwarf. So that's the lifetime of a white dwarf. Is eventually it becomes a black dwarf. All right.
So the other name for this planetary nebula, aside from its NGC number, is the CBS nebula. And
Right.
because
I've heard that before.
it looks like the CBS eyeball, which I don't think they use very much as a logo anymore. But
Actually,
Oh
they
yeah,
do.
I think they still do.
Is
Oh
it?
yeah.
They
It tells
use
you how
a
long
lot.
it's been since I've watched CBS. But that's the CBS nebula. For those that are interested, the processed image that I was showing just a few minutes back, that is 19 30-second images through the 36-inch telescope. So it's just shy of of 10 minutes of exposure time.
But how much processing time, Richard?
A lot more processing time. I had a lot of trouble with this one.
Yeah. But I forgot to bring
But
the
it
cushion.
came out pretty good.
Richard.
Yeah, I needed that cushion. That's right.
Yeah. So
we had a request to look at the Pleiades, and I just wanted to explain why we won't do that. First off, it's getting pretty low in the sky right now, but the Pleiades with this telescope is just too wide an object. It's too big in the sky, and what we would only see is a few of the stars, a few of the brightest stars with this telescope because we're zoomed in so close.
yeah, one of the other things I should mention about the planetary nebula, this is just one of many. There are dozens of them in the night sky. This one is a little bit smaller. There's another one called the Ring Nebula, which is a very popular object to look at for amateur astronomers. There's one called the Clown Face Nebula. There are just a ton of them out there. And they often have very unique shapes to them, to the point where you look at them and you can immediately recognize it because of its shape. So there's, the Ring Nebula looks like a ring out there, although it's actually not a ring. The Ghost Nebula, the blue snowball looks like a little blue ball with another shock wave. Actually, it looks very similar to this, although it's bluer in color. And they're across the whole sky, and these are just stars that are again less than 8 solar masses, and they have reached the end of their lives. And this is how our sun will die in about 6 billion years. So, if you want to see this process up close, just mark your calendar for 6 billion years from now, and enjoy the show.
Does Outlook go that far forward, or do we need to request a feature?
I don't know. You can probably put it on the calendar. I'm not so sure. Speaking of things that we have to wait a long time for, we got a question on Facebook. Can we see the black dwarfs through Nellie or other telescopes?
No.
Well, first off, we don't. I'm not even sure we know where any are. That takes so long to become a black dwarf.
You need a telescope that could look into the far infrared to be able to even detect these. And and Nellie is not that kind of telescope. In fact, for infrared telescopes, the best place to put one is in outer space. And the James Webb telescope that's going to be launched, hopefully sooner rather than later.
Yeah, supposedly this coming fall they're going to launch it.
Hopefully. We'll be able to look into the infrared part of the spectrum. The only infrared telescope I know of in this general vicinity is the Lauschner telescope over in the Orinda Lafayette area here.
There's an infrared telescope on Mauna Kea. But still, they're looking through the atmosphere, so they don't get as clean a view as you would if you were out in space.
But even so, we're talking about black dwarfs, and it takes so long for a white dwarf to cool down that far. I'm not even sure that there are any. They may not exist yet.
Yeah, because white dwarfs glow for a very, very long time. The other thing I wanted to mention is the reason these things were called planetary nebula in the first place is, they were being cataloged back in the 1700s, and really nobody knew what any of these things were, right? But basically the objects in the night sky were categorized as one of 3 or 4 different general types. They were either stars, they were nebula, or they were planets. Now, the nebula that people were most able to easily observe were the ones like M42 or some of the summer Milky Way nebula, like the Swan Nebula or the Lagoon Nebula. They're pretty bright and very modest, or telescopes were able to pick those out easily. But these nebula, they were a little bit harder to see, and the disks that they formed were about the size of planets, but you could kind of tell that they're made out of gas. So hence the name planetary nebula. There wasn't a really good understanding of what the life cycle of these things were and how they came to be, but they were put in their own category, and even though they had nothing to do with planets.
And back in those days, they didn't have much of a concept. If you go back far enough, they didn't even have much of a concept of galaxies. So galaxies were considered nebulas as well in these smaller telescopes. They couldn't determine that they were galaxies.
All right. Well, Richard,
Yeah.
you got two objects on your list that you suggested earlier today. One is the Beehive cluster, and one is the Black Eye galaxy.
Okay. We also got a request online on YouTube, I believe, for M46, which is an open cluster.
All right. Well, I think a cluster is a good idea. That's kind of different from what we've been looking at so far tonight. So either M46 or the Beehive, either one. Your choice. Harold. Wherever you
Okay.
think it's going to be a better slew from where we are now.
Yeah, we just want to make sure we're not washed out by the moon here. So,
Well, M46 ought to be
eh,
all right. It's
yeah, it should be okay. Yeah.
Uh,
All right. Let's let me sync this first.
let's see where this is. Yeah, it's over. It's
I know M40
past the meridian, so it doesn't want to go there.
Whoops. Oh, well, hang on. I mistyped.
Oh, that's in the southwest.
Okay, here we go. All right, it's going to be not too far, about the same elevation.
Yeah.
Kind of right smack in the middle of the less dense part of the Milky Way.
You're going straight there, or are you going to do it?
Yeah, I'm going straight there.
Okay.
I'm being optimistic.
Yeah. Feel lucky?
Yeah. Do you feel lucky, punk?
Oh, we also got a request to look at Sirius for a double, but it's
Oh,
pretty low.
Yeah.
I notice Richard has joined us again tonight.
Yeah.
Thank you for that YouTube video on cleaning the camera sensor. I found the annoying glob on the sensor and was able to clean it off.
Great.
So,
Did you clean
that
off
worked out.
the hot pixel?
Yeah,
that's a little harder to clean off.
I used a fork. Dug them out.
Okay, well,
Yeah.
I see a whole bunch of stars.
Yeah, that's probably it.
Probably because of the narrow field of view of this telescope, we don't really get
Yeah.
a sense of the fact that we're looking at a star cluster here. This is, hundreds, if not thousands of stars that all formed out of a huge cloud of gas and dust. So earlier we were looking at the Orion Nebula, and we were talking about how a big cloud like that is a star forming region. Once the stars have all formed and the gas is dissipated, it leaves behind a cluster of stars all kind of grouped together in the same part of the sky. Roughly the same distance away from us, and of course they're all roughly the same age, and so we call those open star clusters. And the thing that's distinguishing about them is that there's a lot of stars relatively close together in the field of view. The stars run the range in terms of star types. There are low mass stars, there are high mass stars in the cluster. There are hot stars and cool stars. But one of the cool things about open star clusters is that because They all formed out of the same cloud of gas and dust. They're all roughly the same distance away and roughly the same ages, so that characteristics of the stars that we see are intrinsic to the star itself. One star may be dimmer than the other. That star is dimmer not because it is farther away or because we're seeing it through a intervening cloud. It's dimmer because it truly is dimmer. One star may be reddish or orange in color. That tells us it's a cooler star. And it's cooler not because we're looking through a cloud of gas that's blocking some of the light. It's truly a cooler star. And because of that, we use star clusters to learn a lot about stellar evolution and about different types of stars, different masses of stars, and how their characteristics change over time, and what characteristics will help us identify, whether a star is a high mass or a low mass star, whether it's a hot star or a cool star. By studying stars in clusters, we see a range of different types of stars, and we see them all at basically the same point in their lives. So that's really important for us to, develop a model for the evolution of stars based on their mass and their formation out of a cloud of gas and dust. Because it all formed out of the same cloud of gas and dust, they all have relatively the same composition in terms of percentages of materials other than hydrogen and helium. It's mostly hydrogen and helium, but there's a little sprinkling of other elements. And most of these stars will have pretty much the same distribution of those elements. Whereas if I look at another cluster that formed from a different cloud, it may have a slightly different distribution of elements.
Richard pointed out, and I remember this from when we did our Messier, our virtual Messier marathon under the clouds a couple of weeks back, that M46 has a planetary nebula in the same field of view. I don't know if it's actually associated with the cluster or not, but I seem to recall that if you're able to move this image,
I think you want to
move it down and to the right, there's a chance we may be able to
Okay,
see.
I want the stars to move to the right, or I want the camera to move to the right.
The camera to move to the right, and yeah, good point. The camera to move to the right, and the camera to move up.
Oh, the camera to move up.
Up and to the right, yeah.
Okay.
I think. This is
all right. Okay, try it now.
All right.
Yeah, we have to be clear
our 20 seconds.
What it is we want to move,
Probably, any direction would have been equally
move
good
to the west a little bit.
Yeah. We'll see if we can catch it.
Yeah, I think it might be a little more dense. I think we're in a kind of a
sparser part of it.
Sparser part of
this.
But
it was in the
cluster.
upper right edge.
This is a very large cluster, by the way. So
still, the thing I like about this image is you can see that there's differences in the stars.
Oh yeah,
really can. It's pretty neat.
Okay.
Richard says a bit higher and to the right.
Okay, so the camera has to go up and to the right, correct?
Yeah.
I think that's what he means. Yeah.
Okay, got to make that clear.
Maybe a little more.
Okay.
I'm not seeing anything that looks like a.
Yeah, I didn't notice that anything had moved. So
I'm looking at an image.
It moved. It definitely
from Starry Night, but it's so much different. It's so much denser. We may just be in so close that we can't find it here.
Yeah, it's tough on this one. All right. We won't belabor it if we don't get it.
No.
But you can see, even though we have a very small field of view, there's a lot of stars in that field of view.
Yeah.
And you can see that there are differences. The stars are not all the same colors.
I don't see it.
Right.
Oh well.
John, can you see that
Hello.
little string of stars to the left? Do you see anything that matches that in your stellarium
You see
view? Or?
the view of this image is just all stars. It's really very full, so it
Okay.
must be farther out. And I
right.
haven't been able. Well, wait a minute. No, that doesn't make sense. No, I'm not
Okay.
not
Well,
sure
we'll
where
have
we
to
are.
we'll have to take his word for it that it's there.
Have to do a little extra work. Yeah.
Yeah.
Yeah,
Yeah.
we'll have to research this more closely for next year.
Yeah.
Right.
Okay. So how about M64? We wanted to do
Yeah,
that. Yeah.
yeah,
Okay.
that's probably worth trying for
Okay. I'm
if it's
gonna go to
bright enough.
live view. So I'm gonna slew to Denebola so we can synchronize here. So when we make big moves with the telescope, sometimes the telescope doesn't track perfectly. So when it arrives where it thinks we want it to be, it's actually off a little bit. So what we do is we kind of pick a bright star nearby. Are you in live view?
Yeah, give me a sec here. Let me get the shutter
And
right
we
here.
find that bright star and then we kind of center it and then we tell the software that it's centered, and that's what we call that synchronizing the telescope. And
Yeah, I'm not seeing anything.
yeah, I was afraid of that. Okay, I'm going to go back to the moon here for a second.
To the moon, Alice.
Oh no, I'm not going to the moon. One more time. Okay, now I'm going to the moon. You are in live view.
I am in live view, and
Oh, there's the moon.
there's the moon. That's
Looks very rectangular to me.
Yeah,
There we
that's
go.
the moon. Definitely is the moon.
Okay, well that's good news. So we're synced on that. So let's
All
go
right.
back to Denebola.
Is your tracking rate on the
I'm
on
on.
lunar? Or?
I've gone back to sidereal.
Okay.
So just to explain what John was just asking about, for the stars, we have one tracking rate that we use for the telescope.
I saw it go by.
Where? Which way?
It went. You need to move the camera down.
Camera going down. Wow. You sure?
I'm not sure of anything. Let me look through the finder. Yeah, the nebula's way up at the top of the view on the finder.
That's
here.
what I thought. We were going the wrong way.
Yeah. Yeah, keep going. All right, now.
Stop.
Hey,
stop,
there it is.
stop.
There it is. There it is. There it is.
Good.
All right. So anyway, because of the rotation of the Earth, the stars move across the sky, and the telescope is programmed to track the stars as they're moving. But we have to use a different tracking rate for the moon because the moon is orbiting around the Earth. So the moon wants to move from east to west because of the rotation of the Earth, just like the stars move from east to west because of the rotation of the Earth. But because the moon is orbiting around the Earth, that orbital direction is from west to east. So we have to use a different tracking rate when we look at the moon versus when we look at stars. So let me head on over here to M64, the Black Eye Galaxy. Can we still call it the Black Eye Galaxy?
I think so.
Okay. We're
as
on our way.
Nobody punches you in the eye, you'll be all right.
All right. Are we stopped? Yeah. All right.
And then after that, we can go to M3.
Okay. going with a little bit longer exposure here, Gerald,
All
just so
right.
I.
Okay. So the Black Eye Galaxy is a spiral galaxy. It, from our point of view, it's sort of tipped a little bit toward us, so we don't see it face on and we don't see it edge on. We see it at a little bit of an angle. And the Black Eye Galaxy has a very thick cloud of gas and dust, which most spiral galaxies have clouds of gas and dust. This one has a particularly thick one that gives it the appearance of a shiner, a black eye, and hence the name the Black Eye Galaxy. Its other designation is M64. It's one of the Messier objects. Um, and let's see, I think I have some information here about how far away it is.
I have 4.4 million parsecs, or
Okay, multiply that by
14 million light years.
Multiply that. Yeah, okay, there you go.
Boy, that sure got washed out. Let me.
We are not real close to the moon, but we are
Close enough.
Close enough.
Yeah.
Maybe. Yeah.
Problem that you got is that even though we're not pointed at the moon,
I got to do something really crazy here. Hold on for a second.
Moonlight is shining into the tube of the telescope and bouncing around inside there, and that's what is washing it out. Got to talk to Kevin about putting baffles in the telescope.
Yeah. All right. So yeah, in cleaning my sensor, obviously I introduced more gunk.
Yeah.
But what we can see here is the core of the Black Eye Galaxy, and this stripe around it is the characteristic that gives it its name. But that's the best we can do with the moon globe bouncing around inside the tube of the telescope. I'm kind of amazed I could even do this.
Yeah.
Actually, right back up right there looks pretty interesting.
Yeah.
See a little bit of the black eye effect.
Yeah. Yeah.
All right. Well, so much for that.
We tried, folks.
We tried. That was terrible.
We tried.
Yeah.
Sorry about that. Yeah. So another object that's actually a little farther away from the moon, but sort of in the same part of the sky, is M3,
that's a
globular star cluster. So let's go there and see what happens. So a while ago, we were talking about open star clusters, which are groups of stars that all formed out of the same cloud of gas and dust. A globular star cluster is something different. It's a group of several 100,000 stars. They're extremely old stars. They're among the first stars to have formed when our galaxy was forming. And these stars are mostly lower mass stars because the globular star clusters are out in a region of a galaxy called the halo. And the halo is sort of outside the main part of the galaxy. Let me reposition the telescope a little bit here. Shoot another shot.
Yeah.
The halo is, if you imagine the Milky Way galaxy, if you were outside and looking at it, would be a sort of a flat disk with spiral arms in the disk and a central bulge. And around that is a much fainter, more diffuse spherical region, almost spherical region called the halo. And the halo has a lot of old stars in it, and it's where most of these globular star clusters are. So because they're out in the halo, they don't mix it up with the stars that are in the spiral arms and the gas and dust clouds that are in the spiral arms. So they don't have the raw materials to form new stars. So the only stars that are in the globular star clusters are those old stars that formed when they first formed. And because these things are so old, they're more than 10 billion years old, all of the higher mass stars have already reached the end of their lives and have either blown up as supernovae or become white dwarfs, or even some of them may have even reached the black dwarf stage. So the stars that remain are stars that are like our sun in mass or even lower mass than our sun. Um, these stars are all orbiting around the center of the globular star cluster. They orbit in highly elliptical orbits. So they go in close to the center of the cluster, and that's when they're moving very fast. And then they swing out, they go far out towards the periphery of the cluster. That's when they're moving very slow. And then eventually they swing around and they come back in. So they're in these long elliptical orbits that go around the center of the star cluster. And then the cluster itself is orbiting around the galaxy. There are about 150 globular star clusters around our galaxy. Uh, they're all very dense. There's, 100 or several 100,000 stars in a space, maybe only 100 light years across. So just to put that in perspective, the closest star to our sun is about 4 light years away. So if you were to say go 100 light years, spacing stars at 4 light years, you'd only have about 25 stars. But here, across 100 light years, you've got thousands of stars. So that gives you a sense of how much closer together these stars are. If you were on a planet orbiting one of these stars, it's likely you would not have a nighttime because there would be so many stars so close to you that they'd light up your night sky.
So, speaking of our sun, Jim asks, is our sun part of the star cluster? Well, probably at one time.
It was, and we're not sure which one. I've heard some speculation that some of the stars in the Big Dipper may have once been part of the same star cluster as the Earth. I mean, the sun. Yeah. Well, the Earth too.
Well, yeah, I guess you're right.
so it just happens to be that several of the stars in the Big Dipper are about the same distance away from us, about 75 to 80 light years away. So, that sort of suggests that they were certainly part of a cluster. And like I say, I've seen some speculation that the sun might have been part of that same star cluster. But all of the open star clusters, eventually the stars kind of go their separate ways. Because all the stars are orbiting around the galaxy, and they're slightly different distances away from the center of the galaxy. There's a little bit of a differential as far as how much gravity they feel from the galaxy, and that slightly alters their orbital velocity, and that causes those open clusters to slowly spread out, and eventually the stars go their separate ways. But globular star clusters, they stay compact like this. Again, they're out in the outer reaches of the galaxy, and the stars that we still see are all of the much older stars and much lower mass stars that still remain bright enough for us to see from distances, like 25, 30,000 light years away. All right.
Mhm.
Okay. Well, it's a little after 10 o'clock. Do we want to go for anything else, or should we call it a night?
Well, we've got the big plaster ball in the sky, which is limiting our options.
Right.
Yeah.
If you want to pick out a nice double star to close with, that might be nice.
Okay. You want to
yeah.
do that, or M51 is actually pretty high right now.
We could try it. We could try it.
All right.
Let's see what happens.
It's even farther away from the moon, so hang on just a second
All right,
here.
so let's see if we can get a galaxy after all tonight.
Yeah. At least one. We got to do at
Yeah.
least one, right?
Yeah, or try at least one.
Well, we tried one, the black eye, and was a little bit of a disappointment.
Sort of almost.
It kind of gave us a black eye.
Okay, we are there.
All right. Let's see what we can do here. We'll give it a shot.
Oh, I just got an email from Don Saito.
Oh, hi, Don.
He's doing the script for our April Sky This Month program.
Oh, so he's probably not listening right now.
No.
Oh,
Okay, so you're going to do a 50-second exposure here. So M51 is also known as the Whirlpool Galaxy. It's a spiral galaxy that we see almost directly face on, and it's feeding off of another smaller galaxy. And you'll see that hopefully when we get a
We see
nice
anything, yes.
shot of it.
let's see what we end up with here. All right, hold on now. That's not too bad. Let me make this do something here. There we go.
Yeah, I think there's still a little moonlight in this image, but it's not bad.
Yep. Well, we at least see something.
Mm-hmm.
There we go. So
Yeah,
you might
we're
want
a
to.
little off. Yeah, we're gonna
Yeah,
have to
you got to move it down a
reposition.
little bit.
Yeah,
Try
then we
another
might be able to
shot.
see the other galaxy there.
That's right.
Okay.
Try again.
Give it another shot. Seem to recall that I had an image somewhere that we shot with this telescope.
I think I have one of Conrad's. If we,
Yeah, that would be good to show if we.
How long have we been doing this?
we're still new at it.
I'm still not seeing the other galaxy, Gerald. It's got the wrong.
Is that this? Yeah, it's we still got to go higher. Yeah.
All right.
Okay, try it now.
Yeah, I still have to get used to the image scale on this telescope because everything is much bigger.
Yeah, it's also not in the right aspect ratio or
Well, yeah, with respect to the camera, would be nice.
position.
Yeah, rotate the camera a little bit.
Yeah.
Well, while you're doing that, I'm kind of poking around here. I thought I had some of those images that we shot last year of this, but I'm not seeing them.
I have one of Conrad's images right up here ready to go if you want to take a look at it.
Okay, well, we'll try this last one and then we'll
Right.
use that one.
Yeah,
we can end up
wait.
with that.
No, wait. I'm looking right at it, you big dummy.
Oh, there it is. There's the other galaxy. Way up
Yeah.
here. All right.
Yeah, there it is, right at the top of the frame.
Yep.
Wrong way. So you can see the spiral features.
Barely.
And if you look very carefully, you
There we
might
go.
be able
Oh, that's better. Yeah.
Yeah, there you go.
Yeah, you have to move those little handles on the graph.
Yeah,
Just
very carefully.
Very carefully. It's like you really have small movements.
So I'm going to do something here, Richard. I'm going to show a image that we took last year with the astronomical CCD camera.
Oh, very nice.
Same telescope here.
Yeah,
Nice.
that's great.
So this is with the a much longer exposure, actually a stack of several longer exposures taken with a different kind of camera, a camera that's better suited for astrophotography through this telescope here. And you just kind of see all kinds of detail in
Oh
here.
yeah.
Yeah.
Now, some of these stars that you see here, are actually most of the individual stars that you see are actually foreground stars. They're stars in the Milky Way galaxy. But you can see the dark lanes of gas and dust here in the spiral arms. You can see the central core. You can see that the tail end of one of these spiral arms is actually pulling off of this smaller galaxy next to it. Just a whole lot of detail in here. And
Do you remember how many exposures this was?
not off the top of my head, no. I know we did several of them, and then I sent them to you. I plate solved them.
Yeah,
I
that's
plate
right.
solved
I remember
them,
now.
got them all so that they were all aligned correctly, and then I sent them over to you, and then you did your magic with them, and this is the
I
result.
remember this now. Yeah.
Yeah.
Right.
So
Cool.
Okay,
Okay.
well, I have to do Conrad's image just
okay.
Yeah, let's
to
we
show
can close with
Conrad here.
Conrad's image. That sounds like a
Yeah.
good
His,
idea.
his is a color image, so
Yeah.
Yeah. Let's see here. There we go. Can you see that?
Oh yeah.
Oh
there you
yeah,
go.
that's nice. There we go.
Okay.
Conrad this is probably 2 or 3 hours worth of exposure time that Conrad does. And
Yeah, and this isn't even the high definition picture that he had originally. So
yeah.
this was just from our website.
Okay. Well, I think we've exhausted all the possibilities
Yeah,
here.
that's right.
If anybody has any last minute questions, now's the time to hit us with them.
Yeah.
We'll be doing this again next week, starting at 9 o'clock again. And we'll do it every Saturday night if the weather's cooperating. Later on, probably mid-May or so, we will probably have to change our start time to 9:30 because of that darn daylight savings time. And the fact that it gets lighter later or stays lighter later and later at night, eventually, at 9 o'clock, we'll still have a fairly bright sky. So, but right now we'll continue to start at 9 o'clock. And just to remind everybody, you see that donate button at the top of the Facebook page. If you've got a second to give us a donation there, or if you want to go to the Chabot Space and Science Center website, chabotspace.org, and you'll see a donate button at the top of the web page. Please help us out. We're continuing to do all of this virtual programming, not only the Saturday night programming, we do some programming on Friday nights. We also do programming during the daytime, including programming to help local teachers with their students. And we have some other activities. Plus, we're getting started doing our refresh and a little bit of reconstruction here at the Chabot Space and Science Center, getting the facility ready for our grand opening later on this year when COVID goes away and we can finally get back to some semblance of normal. So we do need your continued support. We're not getting the revenue that we would normally get from admissions, so we are relying a lot more on your donations. So if you can take a moment to help us out, we'd really appreciate it. All right.
And I see we've got a lot of thank yous and positive comments in our chat tonight. So I just want to say you're very welcome. We enjoy doing this.
Yeah, we like doing this. It's a lot of fun. But then again, we're astronomers, so. All right. So unless we have any more questions, I think we can wrap it up.
All right. Well, good night, guys. I think that's
good night, everybody.
Okay. Good night.
All right. Take care.